Hi guys, hope all of us are doing great. My name is Ernest. So today's discussion is basically going to be an aspect of the Q value that we had discussed in our first introductory video to decay energy, whereby we had mentioned that the Q value is going to be the energy which is going to be associated with this specific decay process. Now for the beta decay, we are going to see that this specific process can also be regarded to as negatron emission, whereby this is going to be symbolized using this specific a symbol where we were mentioned as with a P negative. We can also be able to give a counter process for that one, which is a positron emission given as such. So basically, we are going to create emphasis in this specific process, and we're going to see how we can be able to represent the Q value for this specific case for the negatron emission. Now, we had given a general expression which was going to represent the concept of a beta decay, whereby we had said that we can be able to give this specific symbol for the general radioisotope, and then we're going to have this given as a product, whereby we're going to have the atomic number increased by 1, which basically is implying the concept of addition of a proton. And then, therefore, we're going to also have a product of the beta negative, or rather, we can be able to just symbolize that one using this negative one given as such. And there was an addition of product of an anti-neutrino given as such in our first case. So therefore, if you try to look at this specific product, the implication is that the proton is going to be added to the nucleus, especially for this daughter nucleus product, which is going to be given as such. So the addition of a proton, we had said that a proton is going to be positively charged. We can be able just to, so this is a proton. This is going to have a positive charge. So the addition of a positive charge in the nucleus is going to result from the, of course, what we refer the decay for a neutron into, of course, a proton, whereby we can be able to give this specific illustration for the general case, whereby we're going to have this one given as this, and then plus an electron. So this is going to be the overall equation which is going to be experienced in this specific case. So therefore, for us to try and look at this, we're going to have an addition proton which is going to be added in this specific nucleus. So for us to observe the laws of conservation of the conservation laws, these charges have got to be, of course, created in a sense that the product, the total number of the charges of the product is equivalent to the total number of charges of the reactants, as we had mentioned. So therefore, we're going to have this particular, therefore, a proton being given by, of course, being balanced by addition of an electron in this specific daughter atom that we have given as Z plus 1. But this aspect of the negatron, which is going to be emitted, given as a B negative 1, which I've given on the board, is going to create an effect whereby we're going to see that there's no aspect of us trying to add an electron in order to offset this positive charge which has been added into the nucleus as such. So this one will play the role of an electron, which we have said, which is going to balance this specific charge that is been included in that specific nucleus. Therefore, we're going to see that the emitted beta particle mass is not going to be included in this specific calculation for the Q value as I've mentioned, and therefore we can be able to give this specific aspect of the Q value, and therefore this is going to have an implication of us not adding the mass. The mass that was added. Of course, we are going to see that for this specific daughter atom that is going to be produced, the effect of a change in mass is not going to be experienced as the influence of this specific electron is going to create that specific daughter nuclei to be neutral. And therefore, in our calculation of the Q values, we're just going to have this one represented as the Q B is equivalent to this specific value for the this mega electron volts for 1 atomic mass, and then the change in mass in this specific case is going to be represented as Z plus 1 minus Z given as such. So therefore, if we have a particular example, then therefore for this one we can be able to consider a case whereby the decay of a free neutron in a vacuum is going to be transformed spontaneously with a half-life of 10.6 minutes to a proton. So in this case, this is just a general question, or a general specific question I'm trying to read, whereby we're going to have a transformation of the neutron to a proton as given in the first case, with the release of this specific negatron or a beta particle. And we're requested to find the cube values of this specific case. We're going to give the respective masses of this by giving it as 931.5. And then we're going to have the mass of this specific first one being given as the mass of this proton, which is going to be 1.00785. So this is going to be 825 minus mass of this specific 0.08665. So the difference between that one, we're going to find the value of 0.782, and this is going to be mega electron volts. So basically for the beta decay, we're just going to consider the mass of the product minus the reactant, whereby in this case we had mentioned that we're going to have this specific representation using this general equation that I've given below. So this one, of course, is going to be more elaborate if we're going to consider the positron emission, and then therefore we are going to contrast it with this specific explanation for this. So catch us in our next video on that, and of course we're going to create a contrast and give it in a more elaborate way, which is going to assist us, of course, understand this specific concept. So that is it for now, guys. Bye, God.